Hello and welcome to today's lecture on reinforcement learning number 9. Before we start with the lecture, I would like to thank you for participating in the evaluation, and I want to quickly go over it. The results of this year's evaluation. There were actually 47 filled responses. The number is not quite correct here. And 40 here, it depends on which part. Nevertheless, so overall, people seem to have liked the lecture so far. So it was mostly, hat sich meistens gelohnt. And the overall grade is 1.92-ish. Okay, so there is still some improvement possible, but it's not too bad. So here what the other students, so just for your reference, what they have found. So the goals are more or less defined, and also what you need to do is also defined. I'm happy that this is good now. Also, I'm also very happy to see that you guys find the topic more and more interesting. Okay, lecture is okay or a little bit difficult. I think that's quite good. Shouldn't be too easy. So I'm also okay with this. And then here are a couple of other things. So everywhere we are on a decent level. There were also some comments. So people liked in principle the homeworks and the project as the final exam substitution, and also that we are covering quite interesting topics. And the recordings are there. That's great. What most didn't like was that these exercises are marked as passed, but then they're actually not passed. So that's kind of confusing. I agree. Now at least we have this notification in the forum that we write when things are trustworthy. We're going to change that next year. Sometimes exercises are too hard, or people didn't like that we have enough introduction to the coding part in the lecture. Yeah, something that we take home and think about, maybe also how to do this more in the tutorials. And the room was one of the biggest thing, and I hope that next year we will just get another one and they start to fix this room. In general, I think also an option is to just calm it down a little bit, because the air and so on is better down here than up there. So today is probably not that bad, but we had different days. Okay, so thanks a lot for all the feedback and the thoughts. We will see what we can do about it. Okay, now today we want to talk about Q-learning actor-critic methods. And so just to give you the context again, so last time we looked into policy gradient methods, so trust region policy optimization and PPO. We also looked at natural gradients. And so this was one way of computing gradients for the policy. And this lecture we want to look at how we can use the Q function to compute gradients for the policy. So this will come to deterministic policy gradient, and then twin delayed deep policy gradient, and at the end we also cover soft actor critic. Next lecture we are going to look into some tricks and stuff to make model-free methods work better in practice. That might be also a little bit of stuff that you can use in the projects. Very good. So today we are actually talking about these methods that I mentioned, and they are state-of-the-art, or like they are still the common choice for continuous control. So this is really very practical. Let's look a little bit of what we did so far. So we had Q-learning, right, as a concept where we have a Q function which we train by TD. So just back up R plus gamma and the next state. There we have here the max operator. That's why this was optimizing for the best local policy. So we can do off-policy learning. And the policy here was implicit. There wasn't really explicit policy. The policy was just the argmax over the Q, right? So I'm checking which value was best. Okay. That's Q-learning. And then we last time looked at this policy gradient, for instance, PPO, and there we have now a policy as a neural network, which is parameterized. We had a value function, which we used to compute the advantage, and then our update was here this score function. So the log, the gradient of the log probabilities of the policy, and so this is then going to change our stochastic policy in this case. So the policy gradient essentially gave us kind of a factor in which direction we should increase or decrease likelihoods of the action that we have just taken. Okay, so and now these have been sort of deep Q learning and also policy gradient essentially optimize the same kind of cost function more or less. You always want to maximize expected future return, and so here are again the equations how we did this. So we had to estimate a Q function. For the deep case, this is parameterized by a deep neural network, and then we just use square loss of our network here and the target, the TD target, yeah? Which I just had on the previous slide. Maybe interestingly here, we typically use an old set of parameters, so like a target network for estimating the next state. Okay, and then the policy was implicit. In the policy gradient, we have this, we learn a Q function or we learn a value function and then getting this advantage. And then we had two options. One was using on policy Monte Carlo and then do off policy correction with importance sampling. And we also used a stochastic policy definition with a neural network here with parameters theta. And then as the objective function that we maximized, we looked into this policy gradient method, which was very flexible. You remember we were able to replace this letter term here, which is now the advantage, with all kinds of different estimators of what an action could be good in. Okay, so now let's compare them. So the Q learning is quite nice because it's off policy. So what does that mean again? Off policy meant I could use data from the past or from another policy to train. And in the most naive setting, it only works in discrete settings because I have this max operator, right? I need to maximize the Q function for this two different places. There are versions which directly use this Q learning and apply this to continuous spaces. For instance, Qt opt, which then uses an optimizer to locally optimize the Q function. So typically we have a value estimation bias because we're using TD learning and function approximation. Exploration is often not too great in these methods because we just use epsilon greedy policy. So taking sort of a different strategy would typically require you to take several times a different action, and that's going to be quite unlikely. In general, these kind of methods are quite good in environments where I have diverse initial states. On the other side, we have the policy gradient method, which is on policy, right? I was able to only use the data that I collected just now with the policy, and afterwards I had to throw this away, so it's quite data inefficient. It requires a stochastic policy. Due to Monte Carlo, it's an unbiased estimator, use unbiased estimation of the value function. But the gradient is not terribly informative because it's essentially just this kind of, okay, increase likelihood or decrease it. It's not as maybe informative as we would like, and we will see how to get there in this lecture. Good, and so typically it's quite okay in high dimensional action spaces, but we will see today that we can do even better, and often it likes environments with low initial state variance. Empirically, exploration often is better in these policy gradient methods because we are changing the policy, and so a little bit of a change in the policy will change the behavior more globally, and so it maybe leads to an exploration of a completely new strategy. Okay, so now let's look at how we can use the Q function better in optimizing our policy. Okay, so first of all, we would like to be more data efficient, right? So this on-policy stuff is not ideal unless we have very cheap ways to collect data. So off-policy learning would be great, and we want to, of course, use it now in continuous domains. So let's see how we can do that. And also something that might be interesting is to just use deterministic policies and not stochastic policies. So now we have this problem, as I mentioned already, that we have the max operator. In two cases in our Q function learning, we have this max operator. We have the max operator, namely in the case where we want to update our policy. So in the first case, for the policy, right, which is just A is arg max over actions of Q, S, and A. And the second part is when we do the Q learning update. So Q update, we have our target is R plus gamma, and then we have here, max A prime, Q, S prime, and A prime. So, 2 times we have to do this max. And if our action space is continuous, how are we going to do this max, right? I mean, it's quite difficult to just find this. So it would involve an optimization problem. And so think about how we can solve this problem, this argmax problem, here in the case where we have continuous control and we want to use a policy for learning our actions. So discuss with your neighbor for 2 minutes or so, and then we'll see whether you found the solution. Not look at the slides. Okay, let's see. Do you guys have some ideas? Anybody wants to speak? Yes?
Maybe you can first use the softmax function to get a probability distribution and this function to get a function.
Okay, so we could use softmax, but that would mean that we have some kind of this categorical actions, no? Softmax would typically take some kind of vector and convert this into a probability distribution. But so this doesn't really work. Let's say if I have a two-dimensional space, but I have continuous actions to move, let's say a robot arm or something.
Can you use the mouse for this, for example, like another distribution?
Okay, we could try to estimate this with a Gaussian distribution and then sample from it. Okay, but then it's still not so clear. Okay, in this case, we would know the maximum, right? And then we are back to our stochastic policy. Maybe we want to keep a deterministic policy, but yeah, could be. Okay. Yes?
Argmax modulus recursion, just take the mode.
Yes, in this case, we just take the mode, yeah. But then we are not so flexible in terms of what the Q function can output, right? So that we are constraining the Q function to work with this Gaussian input, right? So we want to know for which action the Q function gives me the maximum value. And I wouldn't think that the Q function needs to follow a Gaussian, right? Okay, the problem is I think that we don't really have the maximum action, right? So we could somehow maybe sample a lot of actions and see which one is the best one. I mean, that's an option, right? This is some kind of optimization problem. Okay, maybe I'm uncovering some of the ideas. So one option is to imitate this maximum by learning a policy that is trying to learn the maximum. So we can approximate this argmax by gradient descent. So we are essentially looking at this Q function and always go hill upwards, and we will have a look at how this works in a moment. And so we are not actually finding the perfect maximum every time step, but we are sort of walking along the max, and eventually we will find the maximum. And what I said before, the other option would be to actually use some kind of optimizer, which would find an approximate maximization, or like maximum of this Q function, for instance, using cross entropy maximization or other kind of methods. So two papers which do this is the QT-opt and the MPO paper. Okay, so once we have this problem, we can of course also solve problem 2, because this is kind of more or less the same problem. Okay, so now let's see. We want to look at at this number 1 and number 2. This is the thing that we want to explore. So intuitively, we have this picture of the previous algorithms, and now I add here this deterministic policy gradient, and the idea is really simple. I have again this stack: policy, action, and state go into the Q function, and the Q function gives me a value, right? And of course I want this value to be as big as possible, because that means I have a high value for the future. So great. So why don't I just take this Q function and say, let me maximize its output with respect to the action. If I find an action that is going to be better, then in order to give me a higher value, then this is good. So essentially what I do, I train the policy by backpropagating through the Q function and giving me a direction in which the policy has to change. Okay, so in order to understand this deep policy gradient a little bit better, we need to do some notation. So we are now looking at deterministic policies. So in order to make this explicit, I introduce here this notation with this little circle on top. This is our deterministic policy, which gives me a particular action A if I feed in state S. And so mathematically that would be here this Dirac distribution if I express it as a probability distribution. Okay. And now ideally we would like to have this argmax. Of course we can't do that, so now we do this gradient descent as I just said. So the change in my parameter theta, of the policy should be along the direction of my Q function at my current state and where I plug in the policy, and I would like to make this as big as possible, so I just follow the gradient. So here this is my learning rate, then I do an expectation over the states that I'm visiting, and for each of them I'm going up. And so what does it mean here? I have a little bit of a drawing for you. Imagine I'm in a particular state S, I freeze it for the moment, and then I'm checking which of the actions would be better. And I could essentially ask my Q function here for all the different actions, and it gives me the value which might look like this, right? And say we are currently at this point, and then of course my gradient would point in this direction, and I would change my action. I would essentially change the parameters such that I'm not changing the parameters of the Q function, I'm changing the parameters of my policy such that my next action is going to be where the Q function is higher, okay? Do you see a problem with this? Yes?
It heavily depends on our learning rate alpha, so if it's way too big or way too small, we might have problems finding if the actual global maximum.
Absolutely. So as always, when we do gradient descent, we have to tune this learning rate. And then what is happening if we are maybe here, over here, what will then happen? If we start on this side, we go to this local maxima. Of course, gradient descent is only going locally up, so we would then end up with this next best action, but it's not the global best action. Okay, so far so good. So now let's continue. So the intuition is that for every visited state, we make the policy to maximize Q. And so then we get this simple update rule. And now I took this function up here, and we see here our object of interest is inside, namely the policy pi is inside of the Q function, right? This is my action. So this here is the action. And now I'm simply pulling out the inner derivative. So this is the outer derivative, and this is the inner derivative of my policy with respect to the parameter theta taken at the current action. Okay, so this is just backpropagation essentially through this Q function, and that's it. So let's see what these objects are here. So we have this right part, the P1 part. This is the direction of change of actions in order to increase the policy, increase the Q function. So this was this kind of direction that I've drawn in here in this picture. And then the P2 is a Jacobi matrix of our policy with respect to the parameters theta. So how do I need to change my parameters in order to change the actions? And so by just chaining this together, I get here this P1 times P2 is the size of my parameter vector. And so that all works. And so we perform gradient descent here on this Q function. Okay, now let's take this algorithm and understand a little bit better why this is somehow solving the off-policy problem. So normally, right, in Q learning, you remember we have this max operator in order to sort of estimate the Q function for the best action that we can take, and not for maybe a stupid action that our exploration policy is taking. And similarly, we do this here now. So we take this pi circle, which is our policy that tries to be as good as possible. It's deterministic and doesn't do any exploration. This is what we plug into the optimization for the Q function. But then when we run and collect data, we are free to take our policy and make it stochastic. For instance, take my policy and add some exploration noise, then it does some exploration. And then we can still update this. So let's look at the Bellman equation for the Q function in this deterministic case. So we have ST AT, and so the interesting part is in the stochastic case, right? We had to also do the expectation over our policy action, but since the policy here is deterministic, we don't have to do any of this. So our reward and our next state, these are things we don't really have under control, so they are sort of sampled from our environment, but the next action is not anymore part of our optimization. So we get here our reward from the next time step, and we have the Q function with st plus 1, and here we plug in, let me write this, policy st plus 1. Okay, so this part is important because this policy here on the right, this is our substitution for the max operator as we had in the discrete case. So even though maybe our actions that we did here came from another distribution, from some kind of exploration action, in the next time step we assume that we are still following this policy that already knows a little bit how to move on. So clearly it's some kind of approximation to the off-policy version because we are not perfectly taking the max here, but it's a step in the right direction. Exactly. So this is how we made this algorithm of policy by plugging here this deterministic policy in that maximizes the Q function. Let's look how this works for some examples before we are looking into a case into the deep deterministic case. So what do we have to do if you plug in deep networks and so on? Okay, so here these are two very classical examples, mountain car and pendulums swing up. So this mountain car is this little car, I think we had this before, right? You have to steer it forward and backward, and it doesn't really have so much power that it can just directly go to the goal, but it needs to get some momentum first. And on the right we have this pendulum which also needs to be swung up, and it needs to be controlled on this unstable point. And so here let's look at the results. The red curve is this DDPG style. So this is this DPG, this deterministic policy gradient, here with a compatible policy and value function. You remember that we had last time for the natural gradient, right? This kind of parameterization they used here. And this works quite well. In comparison, this second one here is a stochastic actor critic. This is not the soft actor critic method that we are going to present later. This didn't exist at the time yet. So this is essentially similar to it's similar to PPO, but doesn't do any importance weighting. And then this off-puck is a little bit similar to essentially to PPO. Okay, so this already looked good and they were happy about this. So this paper is from 2014, if I'm not mistaken. And the other thing that was interesting now is to think about what is happening when my action space becomes bigger and bigger. And I think this is really an interesting question. So what do you think? Which method is better when the action space becomes big? Is it the PPO gradient or the deterministic policy gradient? Who is for the fact that the PPO one is, or who would think that the PPO gradient is better if the action space is high dimensional? And who thinks the deterministic policy gradient is better? Just a very few. So a lot of people undecided. Okay, let's think about this a bit. So the policy gradient, right, gives us for every rollout that we are getting, a particular action that we take in, it tells us bump up this action or put it down, right? Now we have, let's say, a high dimensional space, let's say 100 actions, and we take 100 action dimensions. So I have 100 muscles or 100 motors, and I can give them a particular value. Okay, I give them a particular value, and then for this particular value, which is 100 dimensional, I get either make this higher or make this lower in probability. So I can essentially kind of, if you want, sort of scale that vector up or shrink it. And ideally in this policy gradient that I directly get from the Q function, I get a vector in which I need to change this action. In all the 100 dimensions, and every dimension I get a different direction. Is that action better, longer or shorter? Like, is it better to have coordinate 1 a stronger action, coordinate 2 is weaker action? So in principle, right, I get a full vector quantity from this derivative to the Q function, whereas in the PPO case I just get essentially a scalar which tells me push up or push down. Let's see whether that is correct. So for this, let's look at a very simple case, namely a bandit, where you remember, we don't really have any state, we just have actions, we do something, we get a return, and that's it. And so let's say we have a reward, which is here defined in this way. So maybe it's a bit weird for you, this notation. So imagine there is a particular best action that we're going to take. This is this A star, which we don't know, or the agent doesn't know. And so we define the distance to this best action, and we computed here this distance function with a metric C. If C is an identity matrix, then this is just a Euclidean distance, but the C can be a particular cost function that shapes the way we measure distances. Okay, so this is something we just specify, and then we let the thing run. Of course, we could just solve this analytically here, but we don't really care because we want to just see whether how these algorithms behave. And now here you see these two cases. So here the dashed line in green is again this PPO style, so this policy gradient style with the stochastic policy gradient. And the red line is the one that uses the deterministic one. And as I already kind of suggested, this is much more powerful. So the error, so on the left is sort of the cost. So how much are we? So this C is actually the reward, but we are measuring the cost. So here you see the minus sign, but the plots are in cost. So the lower the better. And so you see that for 10 dimensions, well, we're already better, but eventually this other gradient also catches up, and then in the case when we have 25 or 15 dimensions, it's 50 dimensions, it gets stronger and stronger, this effect. Good. Having said that, it doesn't mean that in practice people are not using PPO for relatively high dimensional spaces. And it does work, but as you see, it just takes really long time. And so sometimes other properties are maybe more important. But if we can, this deterministic policy gradient seems to be a really good idea. Yes?
Just to ask, what exactly is this? Because C and Q.
Yeah, no, this is part of the problem definition. For simplicity, you can think about C as a unit matrix. That would mean that every action dimension is equal. Every action dimension is equally important for computing the distance. Okay. But it could also be, let's think about it, it's just a diagonal matrix and it has different values on it, positive, so it needs to be positive definite matrix. So that would mean action 1 is maybe not so important in your cost, but action 2 is super important, and so on. And then you could also have off-diagonal elements, which means somehow that this cost function is somehow warped. But yeah, I think it's not super important for the understanding of this problem. In any real-world case, of course, we could have the reward is a very complicated function of our behavior, right, in the world. So this is the most simple thing you could have, right? If reinforcement learning would be so simple to just find a particular action, that would be kind of a little bit boring. Yes?
In this case, for the bandit, the state space is fixed. So when we have more initial variance in the state space, does it still outperform it?
Yeah, so the question was whether if we have higher variance in state space, whether it would still outperform it. So this is now here the plot for a single state, right? There is no different state. And for many different states, now of course it depends a bit on whether our Q function is kind of correctly working. In principle, this should hold for arbitrary states, because for every state individually I'm solving the same problem. I'm solving this optimization problem, which action is the best for that state. And I'm using this Q function. Of course, then there could be maybe other factors which play a role. Okay, good. Bottom line. For high dimensional spaces, deterministic gradient can be much better. I said this already, very good. So now, let's go deep and see what we need to do in order to use high capacity models. So in the original DPG paper, they used this compatible function approximation, and so you are constrained by how the Q function is parameterized, and now we want to use just arbitrary Q functions, and then we get to this what is called deep deterministic policy gradient method. And okay, so what did we do? This is, and also this DPG algorithm already was really just using our policy iteration scheme. So we have our policy is kind of greedy in terms of a gradient ascent on Q plus some noise, and our Q function is trying to fit the Q function of this deterministic policy, and so we are meandering until we are converging, not necessarily to the best possible Q, just because of this local optima and all these kind of problems. So how do we do it? Well, we first need to learn an appropriate Q function. So for this we use, as usual, our square loss. So Q, S, A, and W minus our targets squared, right? This is our typical loss for the Q function, where our targets are coming from TD, right? So this is what we had all the time. So let's just write this down one more time. So RT plus gamma Q S policy and here we need to use the target parameters, and also here in this case we also use target Q. So this is actually in this algorithm not the case, this comes later. So anyway, so importantly here we have the target for our value function, and so then we can just update our parameters for the Q function with gradient descent as usual. Okay, and now this policy pi tilde is, as we said, the greedy policy replacement in Q-learning, and now we are using this update function for our policy parameters, which is the deterministic policy gradient. Here I write mu for the policy that we are actually using to roll out. So this is this behavioral policy, for instance with noise, and then here we have our gradient first through, let's say I'm like to start on the back because somehow this is more obvious how we get there. So we first have to differentiate the Q function with respect to A, and then here we have to differentiate our pi function with respect to theta. So deterministic, did I forget anything? Looks good. right? This was our typical deterministic policy gradient. We backpropagate through the Q function until we are ending up at the parameters of the policy. Okay, so now let's look at this algorithm in the typical algorithm box case. So what do we have? In the input we have our policy network Q. We have the policy, the Q network Q, the policy pi, deterministic policy function, and then we need a replay buffer, right, to collect the data that we have collected, because now we have a policy algorithm. Then we need some kind of random noise process, which we corrupt the actions with to be able to see new stuff, and then we have some parameters, for instance, this tau parameter, which tells us how quick we are updating the targets, which we'll see in a moment. So we have two sets of weights, W and W prime. The W prime is for us the target, which we are keeping for a while. And then we repeat for each episode. We get, of course, state from the environment. Then we take our actions according, now this is important, to our policy plus this noise. Could be standard normal noise, and we will see what else we can do. Then we have to store the stuff in our replay buffer. Then we take this data and update with the mini batch training our Q function according to this update rule here again. So here it's now properly done. So we use the target parameter for the weights and also for the policy. So we are keeping sort of in our target computation, we keep policy and Q function fixed. Then we optimize our policy with the deterministic policy gradient, as we had on the previous slide. And then we slowly change the target function. So here, in some implementations, we had, or in some other earlier stuff, we had fixed target updates. So often you would just override the targets with the current value, and one can also do this smooth version. So there's this parameter tau, which tells how slowly I'm updating this. So the target network always is a little bit lagging behind and acts kind of as a buffer, that I'm not changing this too fast. Are there questions? Yes. What is the random process? Yes, we will discuss it in a moment. So there is, in the DDBG paper, they actually use Ornstein-Ulbeck noise, which is a kind of a Brownian motion that has zero drift, so it comes back to the origin. And you can also use just white noise, so just normal draws from a Gaussian distribution, or you can use another type of noise, which we will discuss next lecture, the pink noise. So there are typical choices one can do, and they have quite a bit of an effect depending on the problem you want to optimize. More questions? Maybe I can phrase this as a question myself. So, in the DQN we had in this line, and in this line we had a different, we had something in addition. Do you remember maybe what that was? So, what happens if your episode terminates? Then, if you're at a terminal state, then you're not allowed to do any backup to the next state, because the next state doesn't really exist, right? You end and that's it. So, you need to store also this done signal, or this signal that the episode is over, and then you would multiply this here with a discount factor that you're not backing up. So this is omitted here for simplicity on this algorithm box, but you would need to implement this in the method. Okay, so let's quickly look at what these different components did do. So the original deterministic policy gradient here with batch normalization is the gray line, and that is performing not too well on this kind of problems. And then we have here a version where we use already the target networks, and this is already essentially this gray line, which is very strong and pretty much as good as if you use both target network and batch norm, which is the green line. These are just two environments, of course. These decisions were made on looking at many environments, and then they decided that this target networks is very important. So this is important is essential essentially, and then this batch norm depends mostly whether you want to use, I guess, pixel inputs and this kind of stuff. So yeah, these were these minor details that I added. So this additive noise is interesting. You have different choices. So this Ornstein-Uhlenbeck noise is one, and the pink noise is another option, which we'll discuss next lecture. Dunflag I also discussed. Of course, the learning can also be done after every episode. You can first collect some data and then do a bigger batch of updates. That is all fine. Okay, and hard updates are also possible instead of this sliding average updates. Yes?
For the learn policy deterministic, will we still add the noise after we're done training to like the final policy?
Yeah. So the question was whether we add a noise once we are done with training, and the answer is no. So we would just use the deterministic policy because that should be the best policy that we have. We have been optimizing against this with the Q function. So typically we wouldn't add any noise. So here are quite some environments that have been used to show that the method works. So over the different kind of systems with a couple of joints. Here this card pendulum, or a gripper that has to grip some object and can move, or a hopper, or this half cheetah, and so on. And I have here a few videos that we can have a look at, or we can just let them run in the break, and you guys can already decide whether you want to get some fresh air or so. So I'll just start them now, and you guys can either enjoy them or decide to take a break. So let me try to open this somewhere. Okay. Well, it takes a moment. I'm in the wrong folder. So this is an implementation of this on half. This is a render policy, and so you see that it doesn't do a lot of stuff. And then we can just let the thing run. Cool. Yeah, and then it's very quick. I think it's cool that they show this random policy because it also tells us sometimes how these environments behave. So this hopper one apparently resets very quickly if you fall backwards. So the random policy resets almost immediately. And so this is now the hopper trained. Okay, so this is this, and the other one is a car racing. I thought this is maybe nice. It's not part of the original paper. I just the videos from the original paper are not available anymore for some reason. So I'm here is some guy used this to train car racing on this torque simulator. Well, at least here it doesn't crash.
Was the input here just a video? Or like the
Honestly, I don't even know. Sorry. I would imagine that it is actually the camera view. Probably some additional privilege information is also fed in, I could imagine. Good, okay guys, so let's make a break for a few minutes. Let's say we meet in 4 minutes and continue. Good. So now let's look at how we can make this algorithm even better. Right? So now we have an algorithm that kind of works, looks good, but it has some problems, and we will see how people have been addressing these problems and make algorithms even more practical and applicable to more problems. So this DDBG algorithm is sometimes quite unstable, and it requires quite a bit of tuning of the parameters, learning rates and these updates and all these kind of things that we have need to be tuned. And so this is not ideal, but the biggest problem is that we have an value overestimation problem, and so we want to look at this first. So in the discrete case of Q-learning, right, our target is, as we had before, this max, right? So this max, and this is okay if we have a tabular case, for instance, or so. But now, if we have a Q function that we learn, then we have the problem that these any kind of little noise that we have on top of our estimation will lead to the following problem, namely that I have sort of an expectation over, let's say, this noise, and I look at now what I do this max over a prime q s prime a prime, and let's say I have an estimation error which I add here to this epsilon, and then this thing is of course always bigger than the direct just the max of q, right? Because as soon as I see this my epsilon goes into the direction of the plus direction, I will use that. So this is a problem, as I'm having function approximators, and they will always introduce a little bit of sort of estimation error, which we can model as some kind of noise. So we could first think, well, maybe this doesn't really happen, right? In the case of DPG, because we are not completely maximizing Q, but we run this gradient descent algorithm on it, so maybe that is not really a problem anymore. But unfortunately, it is. Overestimation does happen. So here is a plot from the paper in here called Addressing Function Approximation Error in Actor-Critic Methods from Fujimoto, and in this paper this is addressed, so looked at. So let's say here we have a run where we run this DDPG on the Hopper environment, and we see here the actual values that we get from our Q function, and the true values would actually live here. So if we would compute the correct values by doing some tricks, we are seeing that there is quite a drastic difference between what is the correct value of Q and the one that we estimate. Of course, wrong Q values can lead to bad behavior, because we kind of think that certain things are good, but they're actually not good. And in particular, it takes, of course, also much longer than to converge, because we first think this is correct, and then after a very long time, we might understand that this is wrong. Yeah, so this value estimation, overestimation is one problem. And of course, we had already one trick here is the target networks. But there's a question first. Mm-hmm.
Last slide. Will show the average value. So it could be that the whole Q function is multiplied by a constant, more or less. Mm-hmm. And the relations between the
Yes, so you're right. So the question is regarding whether this really tells us a lot about the advantage, so the difference between different actions within the Q function, which is the most important thing, right? But of course it tells us also if our Q function in general is kind of wrong, then that's probably not ideal, and we would like to mitigate this. But you're right, it's not necessarily the case that in all algorithms, if your Q function is offset by some value, but the relative difference between the actions is still correct, then we can still get a correct policy. Okay, so now in this paper they look at, yes, there was another question?
Sorry, yeah, question 12, or we can see the diagrams of like each approach. Is it like a policy that is the, like, I don't know, biased object now because of the influence of the next operator, or is it also then the Q network itself?
No, the Q network itself, yeah. So, but it sort of, we see that we have these two aspects. We have the Q function and the policy, and both of them might be sort of too optimistic and think a certain action is good, but maybe that wasn't that good. So now, as we have these two objects here, this policy and the Q function, which are both sort of changing slowly, we use two different policies and two different Q functions, and then update them kind of in some kind of joint way. So we use policy 2 for the TD target of policy of the Q network 1 and vice versa. So here we use so the Y1, which is our target for Q function 1, is R plus gamma, and then we have here Q with value 2, and for the target for the second one is Q, and we have W1. And then here we have the actions which are important, and here we use the policy theta 1, and here we use policy theta 2. Okay, so then if we are continuing with this, then we are still having a problem that our policy 1 optimizes for the Q function 1, so we can have still this over optimization. And so what we do here, we are using a conservative approach where we update this policy according to the minimum of these two Q functions. So here we run this target as the minimum over Q function 1 and Q function 2. So this variant is called clipped double Q learning. So let's see whether this works. So we have now our diagram as before. So the red lines are the ones, the orange lines are the unchanged lines of before, and now we add the blue lines, and so this clipped double Q, you see that we are getting a very nice coherence between the true value of what the Q function should be and what the algorithm itself spits out. So this looks great. And also what is very important is that the true line, which is sort of essentially saying how good we are doing, is also above. So this method seems to actually also work better because we are able to get a higher value. So clipping and double Q can solve this overestimation bias in this Q function. And so then this algorithm, yes? Say again?
Could you repeat why the two truths are different?
The two truths are different because if the algorithm is doing better, so you're having actually a better policy, so the policy gives you a higher return, then your true function should also be higher. So, right, this is not with respect to the same policies, but actually the policies are also trained, of course, in unison here together. Yes? Yeah. So you could use sort of a whole battery of Q functions, and people have tried this with ensemble methods and so on. So there are certain things that you can do. It's interesting that with this 2 already, it's kind of working quite well. I think if you use too many and then use the min, then you can also be too conservative, and so this is a bit of a problem that people have noticed. Yes. Good. Why were we? Yeah, exactly. So now the question is, can we do even better than this? So we have 2 more improvements over the original DDBG. The first one is delayed policy update. So we are also updating the policy after several updates of the critic. So we have a sort of a detachment. The idea is that we first want the critic to really learn the value function for that policy before we are changing the policy. So this is what called delayed policy. And then we also have targets policy smoothing. So this is an idea that now if I have a powerful function approximator and it does this gradient descent on our Q function, and our Q function has this sort of really high peaks here, then I can directly find these peaks, but maybe they are spurious. And so what I do is I add some noise to this policy here, such that I want to make sure that my Q function is the same for slightly different actions, such that everything gets smoothed out and I don't have this very strong peaks. So here I'm adding, this is not the same epsilon that we use for exploration, this is just for this target smoothing, and we use a relatively small noise here, and we also clip it. It needs that it is a bounded noise, so it cannot be unbounded. Yes?
Also employ uncertainty estimates for the Q function to do weight optimization.
Yeah, the question is whether we could do uncertainty estimations, and that certainly is a good idea, and later, like much later than, like people have looked into this for sure, and there are, as I said, for instance, with this ensemble methods, you can do stuff. One can do distributional reinforcement learning, where the entire Q function is treated as a distribution over Q, and so there's tons of stuff one can do. Yes, so taking together this twin, so these 2 Q functions and 2 policies, and this delayed update is giving you twin delayed deep deterministic policy gradient, and because that's so long and people like short names, it is TD3, so T, like twin, and then 3 Ds, okay? So that's why the algorithm is simply called TD3, and it's very, very popular, because it is such a simple method. So here is the performance on a few benchmarks, like again this half cheetah, hopper, and walker, and we see here in blue is TD3, and it is quite nicely performing here on these tasks. Better than, for instance, DDBG, or then they have also their own DDBG, for instance, which you see that sometimes it's much better, sometimes it's worse. So it really depends a bit on the parameters what you do. So in this paper they had their own implementation, and they show both results here. We also see PPO as a result, which is the red line, which is often doing decently, but often takes much longer to converge than these methods, than these off-policy methods. So now let's look at which of these lot of improvements that they did are actually important. So we had this DP is here standing short for delayed policy updates. The target policy smoothing is called this TPS, and clipped double Q is CDQ. And so first of all, we can look at the overall improvement between these two, and you see partially drastic improvement from 800 to 4,000 scores, and in other cases, it's actually through the bank here. It's much better. Then they have their own implementation, which is just abbreviated here AHE. I don't know why, and you see different results. So for some environments, it's already much better than the original one. In other cases, it's worse. And that's how it is if you change certain parameters, I guess. And then because they wanted to do the ablations, they use sort of their own implementation or sort of their own backbone of what they do with the original DDBG loss. And then they see, okay, what happens if I take the original one and add, for instance, delayed policy updates? Yeah, that helps. This actually doesn't help a lot. Here it helps, and here also a bit, and otherwise it gets worse. Then target policy smoothing is something that is helping in some cases, and the clipping is also often you see decremental, and here it helps. So you see the results are not so clear. So it really looks like you have to apply all three together in order to make it much better. Similarly here, we can take the other way around. We can take the original algorithm and start to chop things off. So this ablation here is really well done. And you see if you don't do the delayed policy updates, then in some cases, for instance, the hopper, you get worse, and in the ANT, you get quite a bit worse. In other cases, it doesn't change so much. So you can see that all of these things make, in some environments, a stronger or weaker effect. Okay, we have 15 more minutes. Let's look at one quick example here. Okay, so this is here the bipedal walker. It's another environment. I just thought that I share this with you. At the beginning, of course, there's nothing. After 30, whatever that means, 30 minutes, it's just a video from somebody who has put this online. The walker is not coming very far. This is actually a more challenging environment because it has these ups and downs. And after some time of training, it gets a bit further. You wouldn't maybe say that this is the most optimal way of running here, but at least it seems to become sensitive to the environment and not necessarily fall in every single pit, but eventually does. Good. Yeah, I think now it's sort of managing it. Okay, good.
Does it control the scan line as well?
I think the scan line is automatic, but I'm not 100% sure on that. Okay. Good, so this was TD3. TD3 is really one of the standard algorithms, and it's a good thing to go to because it's so simple, and so there is not so much stuff that can go wrong. It has a deterministic policy, and there are a few tricks that need to be done, but they are not terribly complicated. And so that is clearly an algorithm that should be used as a first sort of stop when doing continuous control. Yes.
As far as I understood, the overestimation bias for the Q values comes from the fact that we select of the arguments.
Mm-hmm. Or like we do here in this case gradient descent on Q, right? Mm-hmm. Mm-hmm.
But as we stabilize this gradient descent in TD3,
Mm-hmm.
shouldn't this problem get also worse? Or is this also already compensated by the method we applied?
So which part do you think gets worse?
The overestimation bias. Maybe this counters. So
I mean, I think the overestimation bias is here countered by this fact that I have these two policies and I'm using
Still is okay, even if I look at even better action. So take the next one.
yeah, so I think the argument would be, if I understand this correctly, is that as we are taking the minimum over these two Q functions, it's quite unlikely that both of these Q functions have the same spurious kind of maximum somewhere. And so I wouldn't really go there and get a value of the Q function which is not yet really grounded in real data, right? So the problem is really you optimize. Okay, maybe to give this a bit more meat is, imagine my Q function looks like this. It goes up here, yeah? So this is Q. I'm here, and let's say I only have ever seen data until this bit. So this is the place where I have seen data. Afterwards, I haven't any a single time tried this action over here. And now my policy gradient tells me to go here. So I will spit out this action. So this is a new action. I will run it. My Q function has not the slightest idea what's going to happen because it just extrapolates. And maybe this is quite bad, but I don't know. And so now I start to take this data that I'm having here, I'm running it, and I'm running this TD update. And before this all sort of, I mean, in principle, you would think, okay, if you just run updates long enough, everything will perfectly converge. But I'm sort of first taking this spuriously wrong Q value and start to update my Q function because I just do the backup before the real value of this action here has propagated through. So maybe in reality, my Q function should look like this here. It should maybe go down, but I haven't really. Oh, this is the wrong pen. I haven't really seen that yet. So I think this is the reason why I get this overestimation, because I go into some new action, I haven't seen it, I think it's superb, I do it, and I already start to update my Q functions with this new action, but actually much later I find out that it wasn't that great. And so if you have two Q functions, then that both of them extrapolate the same way is less likely. Good. Now, in the last part of the lecture, I would like to look at one further algorithm that is sort of now going a little bit back and trying to do stochastic policies again, because they want to solve this exploration problem a little bit better. So, one of the problems with this TD3 and DDBG is that I need a particular noise on my actions in order to explore new stuff, right? I haven't really seen anything, as you know before, you don't know. So that's important. And the other interesting thing is, what happens if in a certain state exploration is really costly and in other states it's not, right? Imagine you are on a cliff. You really don't want to take this exploratory action maybe after you know that this is a cliff, no need to do this anymore. Whereas in other places, you're on a plane, you can just do crazy actions. So you would like to have this much more adaptive. And so the idea is make the policy as varied as possible unless it actually hurts you. And this is what maximum entropy RL comes into play. So the idea is now we are changing the optimization function. So far we always had essentially this part. We always were interested in simply the expected future return. And now we say, well, we want to exactly implement this idea here, be as varied as possible unless it hurts. So we are adding to our reward here the entropy. And so we would like to have as high as possible entropy. And now imagine I'm very varied next to this cliff. So I'm going to incur a high cost. So then my reward, of course, will drop a lot. That's not a good optimization for this function. So the function will need to adapt this variance here on the right, so this entropy, such that I'm still getting the maximum of the two. Okay, and then I have this parameter alpha here that tells me how important is this right part. Okay, good. Yes, important hyperparameter alpha. So the paper is here, Hanoya et al. In also 2018. Good, now let's see how we can do that. We need to do a few things now to implement this. So the first problem that we have is we have to still fit a value function to this now change objective. Before, the value function only cared about our reward. Now it also needs to care about this entropy. And so what do we do now is we go back and decouple our Q function into Q function update from a value function and a value estimation, because this thing here on the right is depending only on the state and not on the action. So we have here this v tilde is the value function for this particular state, and then this value function for this state now depends on the average Q minus the log probability of the action. So this is just directly taking out here from this entropy, right? Formula. So we have here the expectation over action, and so then this log pi directly pops out. And so this is how we can now update our Q function, and we will have a look how this works in practice. So we have these two parts, soft policy evaluation and soft policy improvement. So soft refers to the fact that we have this policy which sort of tries to be as varied as possible. And now we want to still do this gradient descent, but we want to, in order to derive this properly, we want to do the following. We want to make our policy be as close as possible to the following function, namely exponentiated Q. So that means where my Q function is high, I want high probability. When my Q function is low, I want lower probability of action. Right? This is, you can imagine that this makes sense, right? I have now the choice to change my actions, right? I have a probability distribution, and the best thing I can do is I can spread the most likelihood on the actions which are having a high Q, and those which have lower Q, you allocate less probability. And then you just have this normalization constant here, and there would be also some hyperparameter involved of how sharp you want to have this exponentiation. And then you try to bring your policy as close as possible to this one. And so this KL divergence, right, you remember this is one way of us defining this difference between the two distributions, because here we have a parameterized distribution and it may not be able to perfectly match this on the right. Yes?
What about this information projection? So I don't know the term.
Yeah, this is referring to this fact that I'm using the KL divergence as a distance measure between my parametric policy and the distribution that I'm that I can sort of write down explicitly. You will see at the end it actually boils out to, or like comes down to some relatively simple formula, so that's not too complicated. So let's first look at this soft policy evaluation. So I said we are now estimating both a Q function and a value function. So this value function was this Q minus alpha, and so this log probability of my action. And so in order to do this, we have this typical loss functions for the value function here. The first thing is our square loss for the value function, where this is our value network, and here on the right I have my targets, which is the off-policy target. It takes our own Q function estimator and this correction for the entropy term. So this is now our estimation of the value. And then we are fitting our Q function by plugging in the actual TD target is R plus gamma and the next state. And there we are using this value function from up here with the target network, as like with target parameters as before. So instead of just fitting one function, we have to fit two functions, because we need to somehow factor in this aspect of this entropy term. Okay. And now we want to look into this policy improvement step, and for this we need to decide for a particular policy parameterization. So now let's assume we have this Gaussian policy up here. So our policy is simply defining the mean and standard deviation of a normal distribution, right? So my network has one output head for the mean and one output head for the variance or for the standard deviation, and then this is my policy. And then I can also reparameterize this by saying, okay, my policy gets S and a sample from a normal Gaussian in. And so this is the mean plus standard deviation times this epsilon vector here. And so this is how we normally do it in order to do gradient descent on it. And so it turns out that this kind of KL divergence we can minimize by an expectation over the states and a particular noise instantiation. So we sample random from this normal distribution. And here we have now on the right our classical DDBG loss. So this is the Q function with the policy inside. Yeah? And you remember what we just had earlier in the lecture, you just do a gradient ascent on Q. And here on the right we have the likelihood of the policy. And so this is a loss, so this is going to be minimized, and that's why I have here a negative value for the Q, because I'm minimizing it, and this positive value for the log probability. And so this is already it. So at the end, this looks scary, but it wasn't so complicated at the end to actually do this. So if we use this Gaussian policy, then we can write this quite easily, and we can also compute now this gradient here nicely on both sides, because right, if it's parameterized in this way, we can directly see the dependency of theta here in these two terms, and we can directly compute propagate through it. So that's not a problem. For Gaussian distributions, this log probability is also very simply computed, and so this is all nice. Yes, so soft critic learns this soft Q function and soft value and soft Q function, and also is able to perform off policy training. And using this policy as a maximizer for Q as we had it in DDBG. Okay, so now if you look at the results in their paper, of course they are again better than what the other stuff had. They are concurrent actually with TD3, but of course in their paper they are always better. That's always like this. So if you read papers, take them always a bit of grain of salt, and ideally check whether somebody else afterwards represents sort of check these algorithms on some other benchmarks or independently. Soft data critic is indeed quite a strong method and has in many cases this very superior exploration properties and is very good. In some other cases it doesn't perform so well, so that's why in practice it's always good to try them both. Maybe some comments on the method. So there is this alpha, which is the scale of this entropy term, and of course it depends on the rewards, right? If my rewards are very big, then this entropy term has to be scaled, and so that's a bit annoying. So soft data critic in the standard implementation is somehow tuned towards a particular value of the rewards in the thousands, and if you have a system with the rewards of about 1, then you have to change the parameters completely. In order to mitigate this, there is a version where this alpha is also tuned. And yes, I said already, TD3 and soft data critic are de facto standards in continuous control. There are a couple of other methods, for instance, like MPO, maximum a posteriori policy optimization, is often even stronger than those. It's computationally a little bit more heavy, but really quite powerful. And there are good implementations of these methods in, for instance, stable baselines or the tonic RL library or many other of these libraries. with this, we are at the end of the lecture. Do you guys have any questions before we close? No, everybody wants to leave, of course, I understand. Then have a nice afternoon.